For this demo, I'm using 3PO, our portable car hacking demo, to demonstrate some of the CAN attacks that we can do with two of the open source tools that Grim has developed. One of these tools is CANCAT. CANCAT is a tool that Grim has been developing for a few years now. It is an Arduino Due with a CAN shield. It is more of your common car hacking tool. We use it for doing CAN bus and packet injection, CAN bus sniffing. The one disadvantage that CANCAT has, though, is it is built on top of a standard CAN peripheral. So it's limited in how badly we can misbehave with that, which I'll demonstrate a little bit later. The other tool is the CANT tool that Grim recently released. CANT is a Nucleo H743ZI development board with a CAN transceiver wired to it, and we use that to essentially bitbang CAN over GPIO. This gives us complete control over the CAN messaging at the electrical level and allows us much greater control over what is going out on the CAN bus. We're going to start the demo by showing how to use CANT to act as a bus killer. What this attack does is any time any node on the bus tries to send a message, CANT will take over and send a message, a valid CAN message with an arbitration ID of 0. This limits any other node from transmitting on the CAN bus. So we'll go ahead and set up that attack, set the baud rate, and we'll go ahead and choose the bus killer attack. And we see that very quickly our brake fluid light pops up, the instrument cluster starts shutting down. Currently nothing is able to transmit on this bus. If we come over here to the oscilloscope, we see that we're sending out it's a valid CAN message. If you decoded this, it would be a completely valid message. But it's always sending this message whenever any other bus tries to send its own message, effectively killing the CAN bus. Now, the effect of this isn't all that much different than you'd get from jamming a paperclip into the CAN bus and shorting the two wires. The advantage of CANT's approach is that it has that same effect without violating any of the rules of the CAN bus. This is a perfectly valid, properly functioning CAN bus, just nobody else is allowed to transmit on it. Go ahead and stop this attack from happening. See that the CAN bus goes back to normal on the oscilloscope. Next step is we're going to illustrate those differences I was talking about between how CANCAT works and how CANT works. So CANCAT is a tool we've been developing for a while, like I mentioned. It runs on the Arduino Due with a CAN shield on it using a standard CAN peripheral. So it allows us to do things like just send a CAN packet. What this CAN packet that I'm about to send does is it causes the brake fluid low light to come on. And we'll see that happen up in the instrument cluster. I'll send it, brake fluid low pops up, but only for a fraction of a second. And this is because the body control module is sending out the brake fluid status message about 3 times a second. And of course the brake fluid level is actually okay on our demo. So this message that we're injecting is being overridden by the body control module almost immediately once we send it. If we try to flood the bus with this message, just put this in a while loop and keep pounding on it, we see that the brake fluid light will pop up and go away, and pop up and go away, and pop up and go away. This gives us very herky-jerky control over whatever it is we are trying to control. This is a problem that you run into quite frequently with CAN. You're trying to inject a message to do something malicious, but your message is getting overridden by a different ECU on the system. CANT has a very nice data replacement tool mode that has been written. We'll go ahead and set the arbitration ID. The arbitration ID is 290. We'll set the baud rate to 125 kilobits per second. And we'll choose the data replacer attack. Well, the data is 8 bytes long. And if we go back, we'll see the message is 8800010600000000. We'll go 88000106000000. And as soon as we start doing this, we see that our brake fluid level low light comes on in the instrument cluster and stays on. And the reason for this is because this attack, since we're replacing the data with our own data, violating the rules of CAN, but we're only violating the rules of the CAN bus from the perspective of the body control module. The body control module should be the one sending the message, should be the only one on the bus, but we're taking the bus away from the body control module. So the body control module is going into an error state. If we take a look at the scope here, we'll see somewhere along in here. Right here, we see that the body control module is sending out these longer pulses. These are error frames. The error frames we were discussing earlier. And we'll see there's quite a few of them. If you count them up, there should be 16 of them. Because the body control module is going into its bus off state, resetting, sending active error frames until it accumulates 128 send errors again. And once it's accumulated those 128 send errors, it goes into error passive and then eventually into bus off. So CANT allows us to then just override any message on the bus, eventually knocking that ECU offline to allow us to have complete control over whatever message it is we are trying to control. The last attack I want to demonstrate is an attack of the overload inserter attack. So the overload frame jumped out at me when I was reading the CAN specification. The CAN spec says that no device on the bus should send more than 2 overload frames. But it doesn't say what should happen if somebody does send more than 2 overload frames. Now, the purpose of the overload frame is to allow slower nodes on the CAN bus to request a little bit of extra processing time after they receive a message. So they send out the overload frame. This gives them just a little bit more time to process the message that they've received. Let's go ahead and set the baud rate again and choose the overload inserter. Let's send 2 overload frames. Just behave in a nice appropriate manner. And we see that things seem to be functioning quite normally. If we come over here to the oscilloscope, we go in, we see, yep, we have 1, 2 overload frames. Everything looks nice and kosher. Let's send more. Let's send 5 overload frames. See what happens. Come back over here to the scope. We see we have our 1, 2, 3, 4, 5 overload frames. And we also see that everything still seems to be running properly. So apparently sending more than 2 overload frames doesn't immediately cause any issues. Let's try sending more. Let's try sending 50 of these overload frames. We'll send quite a few. Now we see that this is taking some effect. The brake fluid level low light comes on for some reason, and that it's not a camera glitch. That instrument cluster really is kind of dimming. You can still see it's still kind of running, but it's definitely something weird's going on. And if we come over here to the oscilloscope, we see, as we expect, that we're sending a whole bunch of overload frames. We can also see that the amount of time we're spending sending overload frames is vastly more than we're sending actual messages. So we're actually seeing a significant increase in bus loading here. We're going to send more. Let's try sending 100 of these things. No, 1,000. Send 1,000 of these things. And instead of sending 1,000 causes the instrument cluster to completely shut off at this point. And if we come back here to the scope, have to zoom out quite a bit, we see we're spending very little time actually sending messages, and we're almost spending the entire bus time is spent in these overload frames. This is a demonstration of CANT, what CANT allows you to do. CANT allows you to do things that you can't do, and see what the effects of that is.